let's plot the overdamped and critically damped setups in Mathematica. And I have not forgotten that we still need to fill in the general solution for underdamping. Okay, so we've got x of t equals c1 exponential of some big thing times t plus c2 exponential of some big thing times t. And now I just need to type in the big thing. So I've got minus gamma plus the square root of gamma squared minus 4mk all over 2m. And my handwriting there is terrible, so let me go back here and make sure it's correct. Okay, and then I can just copy and paste that here with a minus sign. Okay, so that's x of t, and as you might imagine, it's not going to be able to plot x of t, no way, since it has no idea what gamma and m and k are, so how can it evaluate x of any particular number and get a particular number? But let me get the code in place for plotting. Okay, so there's our plot, or lack of plot. Now, let me zoom out a little bit. Let's just choose some values for m and k and gamma. So let me choose m and k first. So m is the mass of the object at the end of the spring, right? So what should I choose? Well, it kind of doesn't matter, actually, because I never specified units at all in this whole setup. I mean, m does have units, it has units of mass, but I didn't say which units of mass. It doesn't really matter, as long as you use consistent units throughout. The equation is going to be the same. So, of course, if you want to get things down to precise numbers with the units that you want in the end, then you need to use those units. But just to observe the dynamics, it's not too important. So I'm just going to set mass to be 1. Okay, another justification for that setting mass equal to 1 still shows you the full story, is that I haven't said which units of mass I'm using, but suppose the object at the end of the spring has mass 7 kilograms. Then couldn't I just invent a new unit, like call it gilograms or something like that, and just define that 1 gilogram is 7 kilograms? Then the mass is 1, right? So you can just choose the units to make certain things be 1, or be whatever nice number you want. I guess not 0, right? You can't just zero things out that way, since 0 in any units is going to be 0 in any other units. Okay, but you get the idea. So I can set the mass to be 1, and it will show me enough of what's going on. Okay, and what about the spring constant, the spring stiffness? For similar but more complicated reasons, I can also arrange units so that ends up being 1. So what are the actual units of spring stiffness? This is actually worth a small digression. So what are the units of K? Well, where does K show up? It shows up in the Hooke's law, that the force is negative kx. The restoring force is negative k times the displacement from equilibrium. So this has units of force. So if you're using like standard units or whatever, the favorite units in physics courses, it would be newtons. So this would have units of newtons. And if this has units of meters, say, then K would have units of newtons per meter. So that would be the units of K. Units of force per units of distance. But, I mean, units of force are themselves, like newtons are just made out of other units. So like a Newton is going to be a kilogram meter per second, right? Something like that, however you want to arrange it, meter per second squared. So it's going to be something like that. So in other words, look at it like this. It's a unit of mass times a unit of distance divided by your time units twice. We can choose the units of mass so as to choose to make the mass of the object at the end of the spring be 1. And by the way, the m here is not, don't confuse those m's. This m is meters, not mass. But we have not specified our choice of units for time or for distance. So we could just choose either of those. So that I could say, for example, I could say afterwards, then choose, instead of meters, use a different unit of distance to make k be 1. You know, make the spring stiffness be 1. We can do that. Just measure your distance to force it to be 1, whatever it was. Use those units of distance. Then you're still left with even freedom to choose what units of time you want to use. So we could choose our units of time to be seconds freely, and still end up having m equals 1 and k equals 1. Where was I? There. Okay, so I can just do this, and I'm not missing out on any interesting stuff that could be going on. Okay, so now let me do my plot. Okay, it still doesn't work. Of course, because I have not chosen gamma. Well, can I just choose gamma equals 1? Could I just set gamma equal to 1, and that will show me the full story by the same arguments that I just made? No, that cannot be done. Why? What are the units of gamma anyway? So damping force is gamma x prime, right? So that means this is a force. So the units of gamma, so this has to have units of newtons or whatever are the units of force, which will not be newtons if we arrange our units so that different things are 1. But this will have to have units of force. Let me just use newtons as a stand-in for that. Then gamma will have to have units of force per unit velocity. So gamma will be in newtons per meter per second, something like that, except it wouldn't be meters. It would be whatever units of distance we ended up choosing back here to force k to be 1. Okay, so maybe a better way to write it is going to be force distance per time. So filling in what are the units of force. Force is like mass, distance, time squared, right? And then I'm dividing by distance per time. So a bunch of cancellations. Distance, time in the denominator here, time squared. So I've got mass per unit time. So the units of gamma are units of, I actually didn't know what they were until I did this just now. The units of gamma are units of mass per unit time. Interesting. So actually, couldn't I just scale my units of time in order to force gamma to be any number I want? I'm a little bit surprised by that. Did I make a mistake here? Okay, I had just paused to try to find my mistake. Yes, I made a mistake determining what are the units of k. It actually does not make sense to choose units of distance to make to force k to be 1, since k is units of force divided by units of distance. So the units of distance are going to get killed off in the choice of k. So if I were to, I think this discussion needs to be done more carefully. The units of k, so it's true, units of k are units of force per unit distance, force over distance. And that means, force is mass, distance times squared, and then here over distance. And you see, for some reason I dropped this distance from the denominator. I think I was just thinking about the units of force rather than thinking about the units of k. So yeah, actually the units of k are going to be in mass per time squared. So yeah, if you choose your units of mass, where did I put it? Oh, I already erased it. So choose units of mass to, let me write it like this, save some writing. Choose, this means the units of mass, choose the units of mass so that m, the mass at the end of the spring in our specific system, is actually 1. Choose units of time. You see, there's no distance here. So this is the units of k, is this. Units of mass are now fixed. They're chosen to make m be 1. So now I have to choose the units of time. So it cannot necessarily be seconds. Choose units of time so that k equals 1. Okay, now look at the analysis for gamma. Gamma is in units of mass per unit time, but both of those units have already been chosen. So I cannot then also go and choose that gamma is 1. So it's possible to make choices about units to make mass be 1, to make k be 1, but not to make mass be 1, k be 1, and gamma be 1. And hopefully that's not surprising, because we saw that depending on whether gamma is big, in between, or small, we do actually get like drastically different things going on. So just setting everything to 1 and saying that that's the whole story, well, that's just, when you set everything to 1, that's going to be one of the cases, right? I guess it would be case 3 if you set everything to 1, because 1 is less than 4. Okay, back to the plots. So gamma I cannot necessarily set to any particular thing and think that I am fully understanding the system. So I can choose one thing for the moment and see an example. Well, no, not one. I can choose one large enough gamma and see an example. What's going on? I need to choose C1 and C2 also. Yeah, let me make those bars that I can manipulate. Okay, so there's some bars that you can manipulate for C1 and C2. And yeah, you see basically exponential decay. So as I vary C1 and C2, I'm changing the initial conditions. But it's not very clear how. I mean, some choices also look kind of interesting. You get it crossing the equilibrium and then coming back. If you run it for long enough, you always get, no matter what C1 and C2 were chosen, it's always going to, in the long run, go to 0. That's because the system's always losing energy. If there's any gamma at all, then eventually the spring is just going to, the mass is just going to settle towards the equilibrium. Yeah, so C1 and C2 are not very easy to interpret what they're actually doing, or what they physically mean, because they're related to the initial conditions, like the initial position and initial velocity of the spring, but it's not obvious how they're related to the initial conditions. So it would be nice to replace this picture by one where, as I manipulate the bars here, I'm actually directly controlling the initial position and the initial velocity of the mass. So there is a way to do that, and yeah, as you can see, I somewhere in the cutting of the video, I had to put in C1 and C2 as though they're arguments here, because probably there's a more elegant way to do this, but as far as my Mathematica knowledge goes, this is a way to ensure that C1 and C2 can be manipulated inside these bars here. Okay, so let's see, how are these related to the initial, how are C1 and C2 related to the initial, let's say x naught is the initial position, x naught, and the initial velocity would be the derivative of, well, let's figure that out in a moment. So this is the relationship between the initial velocity and the initial position, x naught, and C1 and C2. So this is what comes out of just taking this and plugging in t equals 0. You just get C1 plus C2, right? So that should be the initial position. And what about the initial velocity? So you can take derivatives in Mathematica, and this is how I can say I want to take the derivative of this function as a function of t, take the derivative with respect to t. Then I get this. Then if I want to go and plug in t equals 0 into that, then I get this. So this apparently, what came out here, apparently is what is the initial velocity, which I'm calling v naught. So see these two equations? These are the relationship between C1, C2 and the initial conditions. So one thing I can do is solve this system of equations. So I'm just going to copy and paste them in, which is a crude way to do things, but at least you can see clearly what I'm doing. And solve for C1 and C2. And here we are. C1 is exactly this in terms of x naught and v naught, and C2 is exactly this. So this is just solving a linear system. You can do this by hand, but it just is annoying, right? Solving a 2x2 linear system by hand. It's not that fun. Okay, so one thing I can do is use this as my C1. So go back up here. So let me copy this stuff, put it down here. And then for C1, I'll use this expression that involves basically this more complicated way of writing C1. And for C2, I'll write this more complicated way of writing C2. And I'll view this as allowing me to manipulate, instead of C1 and C2, x naught and v naught, the initial position and velocity. And that's what I'll manipulate in the end here. So let's see. So let's allow you to change to so the initial position, that's like how far you can pull the spring out before you let go of it. So let's say you can pull it out 0, or you can pull it out up to 4, and the vertical plot range is 5, so that'll fit. And v naught is like, if that's 0, then you're just releasing it from rest, and then whatever you choose for v naught, that determines whether you're going to actually flick it forward or throw it backward. So let's allow this to range from -3 to 3, and look at what we get. So as I change x naught, this is kind of the expected behavior. So down here, this is x naught equals 0. Okay, let me not run this out for time 100. Let's run it out to time like, how about 3? 5. Okay, so right here is x naught equals 0. And as I change x naught, you see what's changing? Like when I say x naught is 2, right now it's about 2, that's where it starts. So that's where I'm releasing the mass from. And what does it do? It just goes back to equilibrium. So this is time on the horizontal, x on the vertical, right? So this is representing the mass just goes back to equilibrium over time, and it kind of slows its approach as it approaches. So dragging this basically just drags this handle up and down from 0 up to 4. The initial velocity, this is like the slope. So right now it's set to -3. Let's set it to 0. So that's like releasing from rest. And these are the different things you can have. It's kind of fun. And if you want to, you can make the initial velocity positive, which means you're sort of pulling it, and then instead of releasing from rest, you're throwing it further out away from equilibrium. So what happens if you pull it and then throw it further out away from equilibrium, then it goes that way for a little bit and then comes back. So this is why you see a bump, goes and then comes back. It's very cool to see this stuff actually work and give you results that you would intuitively expect. Okay, and what about underdamping? So, oh yeah, what about critical damping? Let's see a plot of that. So going back up here, I would have to set gamma to be, so if m is 1 and k is 1, what is the critically damped case? It's the case where gamma squared is 4mk. So gamma squared is 4, in other words, gamma is 2. So for us, where we've chosen units of space and time so that m and k are 1, gamma equals 2 is the perfect value of gamma that is perfectly between overdamping and underdamping. Okay, so this is what critical damping looks like. And again, manipulating C1 and C2 like this, it's not so straightforward to interpret exactly what it is we're changing. So I might go here and figure out how C1 and C2 are related to X0 and V0, which changed because how I did it initially depended on my choice of gamma, which I have changed. So I've got different equations here. So the first equation didn't change, it seems, but this one changed. Solve those. Aha, of course. In the critically damped case, this is no longer correct. So, okay, so you see solving gave me nothing out. This is actually a pretty good lesson here. This is what happens when you do not use linearly independent functions. So when I set gamma to be 2, this portion in the square root became 0, right? That's the whole point. And so these are the same function here and here. And so when I went to try to satisfy some initial conditions, I ended up with the same equation. These two equations, so not the same equation, but the left-hand sides here are dependent. Yeah, so there's no solution in general. So that's why we want linearly independent solutions, and we have learned the way to deal with this is multiply one of them by t, and then it'll work. And I actually don't need to put this, right? Since that's just 0. I can put it. I'll just leave it, but it is just 0, so I can just delete it. Okay, there's the actual critically damped case. This is what it looks like. What I showed before was wrong then for the critical damping. Yeah, so it's kind of interesting. It gives you this one yeah, I don't know how I don't have anything to say that's really useful about what it looks like. So let's go back here and work this out, So now C1 is just X0. So that's nice. Not a very hard equation to solve, but I'm lazy and I'd rather copy and paste things. Okay, so C1 is X0, big surprise. So here I added in a t, right? Okay. And this used to say C1. Let me just copy from up there. No, that'll take too long to change everything. Yeah, so this used to say C1. Now it'll say x naught. Okay, this used to say, yeah, this one used to say C2. Now it will say V naught plus x naught. Okay, now, and I need to change this to 2, which is what we had up there. This is not the cleanest code here, but it gets the job done. So here I'm changing the initial position, the initial displacement of the mass from between 0 and 4. So 0, 4. So let's say I pull it out all the way to about 3, and then I let it go from rest. Then this is apparently what happens in the critically damped case. And if I pull it out to 3 and then throw it further outward, then I get something like this. So it looks pretty similar in the end to the overdamped case, I would say. If you run it for a very long time, so this is really something we should do, then you see that while there might be some interesting junk going on at the beginning, it's just going to eventually go to 0. So all the interesting stuff is very temporary. If you let time run long enough, everything goes to 0. That's the case for critically damped and overdamped cases. Okay, well, the most interesting case is going to be the underdamped case. And that, I think this video has run for too long, so let me do that in the next video.